Hey, thanks for joining me for your calculus enhancement. We are going to look at arc length and surfaces of revolution. So this is part one, and in this we're going to talk about how we go about deriving the formula to find arc length, right? So this is kind of the idea here. I call it a path. To find the length of the path of f from A to B. And the page moved my dot. Alright, so there. So how do we find this path? Once we do, or the length of that path, excuse me, from the point A, f of A, to B, f of B, right? This point to this point. And once we do that, in the next video, we will find the surface area generated by revolving this path. Maybe, something like this. Let's see if I can kind of do this. Are you kidding me? Let's say the marker doesn't want to work as soon as we start doing this. So something like this. Let's see. Alright. Did I do that right? No. No. Whatever. So we're gonna in the last videos we made for last week, we found volumes of revolution. Now we're finding the surface of revolution, the surface area. Okay? And so first two preliminaries, some theorems that we skipped over from chapter 3 when we ran out of time. Really two basic but very important theorems. First, Rolle's theorem says let f be continuous on AB and differentiable on AB. So that means its derivative exists. Remember that derivatives, to calculate a derivative, we have to take a limit from both sides. So I will get to, when I go to the other board, something that's not differentiable on an interval. But for this, you can just think of, its derivative exists. And a little drawing here of Rolle's theorem. We just have some function. It's continuous and it's differentiable, and f of A happens to be equal to f of B here. Right? They have the same value, maybe I'll call it D. Okay, and all that Rolle's theorem is saying is that if f of A is equal to B, there has to be one C in this interval somewhere where the derivative is 0. And you could find this by just trying to draw some continuous things. For instance, I will just draw a funny thing there. Okay, look at this function has 3 c's. That'd be c sub 1 maybe. This would be c sub 2, and right here maybe c sub 3. 3 places where the derivative is equal to 0. I think that's fairly intuitive and obvious. But I will include a proof of Rolle's theorem as well as a proof of the mean value theorem, which is proved with the help of Rolle's theorem. This one's even better. The mean value theorem, I put in brackets here. This is our hypothesis, our assumption, and so this is still true over here. We have a function continuous on a closed interval, differentiable on an open interval. And now what we have here, this is a very interesting one. I'm just going to draw some random function here. Not random, I guess it has to be continuous and differentiable, right? But so there we go. I'm going to look at, to make sense of this problem, let's just start looking at the equation there that is in the theorem. Okay, so first off, what is f of b minus f of a over b minus a? Well, goodness, that's just the slope of this line. A line that connects two curves, or a line that intersects a curve in two places, we call a secant line. Right, I'm just going to let that go up there. So this is the slope of the secant line, right? Change in y, f of b minus f of a over change in x, b minus a. And all that's saying then that there has to be one c in this interval somewhere, at least one, where if we evaluate the derivative there, we will have precisely the same slope. All right, this is a really nice one. you know, the implications of this are kind of interesting. I'll show you a couple problems with some interesting implications. But you know, if you drive from here to Livingston with an average speed of 67 miles per hour, at some point you went exactly 67 miles per hour. That may seem obvious. Okay. Back over here, a new definition. A function f is said to be continuously differentiable. This is an interesting word. The first time I heard it, I thought, continuously differentiable. You can just take its derivative forever and ever and ever. Well, that's not what it means. There is something like that, but that's a different term. So a function f is said to be continuously differentiable on a closed interval if f prime is continuous on a closed interval. Okay? If a function's derivative is continuous on a closed interval, then the graph is smooth. So I guess I'll give you a couple non-examples. One you're really familiar with, maybe the absolute value of x minus 1. What does its graph look like? Well, what does its derivative look like? We'll say this is x, this is f over here. I will draw f prime and x. Well, what is the slope to the right of x equal 1? It's minus 1. And the slope to the right of x equals 1 is positive 1, right? That function is not continuous there. Or the derivative is not continuous on the interval, and therefore it's not a smooth curve, right? Some other words we use for these kind of things are cusps or nodes, maybe where there's discontinuities in the derivative, something like this, right? It is going to have, that is not a smooth curve, and if we look at the graph of its derivative, we can see that it's becoming very steep here, so its function is going to be very, very positive to the left of C and steeply negative to the right. So that is a discontinuity in the derivative, so the function is not continuously differentiable. Right? Simple term. Know that for what we are doing, though, we have to have smooth curves. We have to have functions that are continuously differentiable. So, well, how might I go about finding the length of a curve? Well, if you've been watching us do areas of rectangles and things like this, and what the heck did we do last time? Oh, yes, finding the area of all these little washers and discs, then this idea. We're going to split this interval from A to B. We're going to attempt to find the length of the curve on here. We will call it S. And what we do is we just kind of split it into n intervals. And because from here to here, we can get a good approximation of the curve, right? From there to there, we can get a good approximation. From here to here, from here to here, and so forth. And they're called straight line approximations, but we have a formula for it. And let's see here. Let me make sure I use my right notation. We will do this. We will say that the length of the curve S is approximately, and we're just going to add up all these little guys. We're going to say it's a summation from I equals 1 to n, and how do we do this? We do the distance formula, right? x2 minus x1 plus y2, Let me write it over here as you know it, because I'm trying to say it and put it in the language I want to. But as we used it in geometry and all the time since, it is the square root of x2 minus x1 squared plus y1, y2 minus y1 squared. Sorry. Yeah, that's it. So what are we going to do here is we have all these little delta x's, and so we're going to sum up each one, right? The delta x of 1 squared. That is going to be this length. I will call that delta x1 here, actually. Let's change those numbers. Right, from x to 0 to x sub 1, that's the change in delta x. This is the change in y, or that's the change in x from x sub 0 to x sub 1, and this is the change in y. And this is a right angle, so we can get this guy by using the Pythagorean theorem. All right? Delta y. Okay. That should be an I as well. Okay, so we keep summing up. We keep finding the square root of the sum of the squares of these lengths, and we keep finding that hypotenuse all along. And we keep doing that. And now we just do some fancy algebra. Watch this. I can also approximate it like then from the summation from I equals 1 to n. I'm going to pull this out. I'm going to say the square root. I'm going to pull out a delta x squared. Forgot that squared, didn't I? You guys knew that. You were hollering at me. And then what I have is 1 plus delta y sub I over delta x sub I squared. Okay? So look at that. Make sure that you realize I have the same thing there. And yep, you're okay with that. And then so remember that a square root of products can be written as a product of square roots. So I'm going to rewrite it as a summation from I equals 1 to n. I'm going to pull this guy out, take the square root, and we get delta x sub I times the square root of 1 plus delta y sub I over delta x sub I. And I'm going to write it like that now. Really, I should have probably done this. Maybe my parentheses are a little confusing there, sorry. I will shut up for a second so you can see. That looks better to me. You okay with that? Okay, so remember that we said over here that f prime is continuous on this interval, and if it's continuous, then this derivative exists for every x in each of one of these. For each one of these x's in each interval, the derivative exists. We said that f prime is continuous. It's continuously differentiable. And then we can invoke the mean value theorem. The mean value theorem says there's a c sub I in each one of these intervals. And right here, right? Right here, there's a c sub I in each one of these intervals that we can calculate that derivative exactly at. And that means, of course, since we're on this interval, that the derivative f prime of ci, or f prime at ci is f of x sub I minus f of x sub I minus 1. This is change in y over change in x, right? But that is also change in y over change in x. And you see it? That's the same thing. So I can, this is the derivative. Okay? And so I ran out of room, and so I'm going to have to come over here. I'm going to take this s again, and I'm going to say s, the length, is equal to the limit as n goes to infinity of the summation from n equals 1 to infinity of, and I'm going to use my commutative property and write 1 plus f prime of c sub I squared times all these little delta x's. But this, of course, will look just like something you've seen before, right? This is what we've been doing all along for the summation. This is what we first did when we first found area and when we found volume. If we let, this is called a Riemann sum, by the way, you're going to hear that word in Calc 2, Riemann sum. If we let this guy go to infinity, that is the same as taking the integral from a to b of the square root of 1 plus f prime of x squared with respect to x. And there you go. That is the formula for arc length. I'm gonna run out of room. Just too much to write, too much to say. So, a relatively simply derived, you can see that it might perhaps get nasty, and so probably some of the problems that we'll ask you to do by evaluating the integrals by hand will probably be maybe, these little cooked up problems that Elijah likes so much when he says, obviously somebody already knows the answer to this. In theory, of course, you guys that are going to be doing some higher mathematics and really finding these kind of things, you're going to have a lot of software at your disposal, and so they're good at that kind of stuff, right? It doesn't get too messy. Okay, that's it for now. The next video, we'll start right off with arc length, and then we'll rotate the path around about the x-axis to create a surface, and we'll find its area. Okay? Love you guys.